All right, so today's notes are on linear programming. Our content objective is to solve problems using linear programming, and our language objective is to use the correct terminology to explain linear programming, including constraint, feasible region, and objective function. So I'm going to start by defining some of those terms. So linear programming, what we're learning about today, is a method for finding a maximum or minimum value of some quantity given a set of constraints. So what this means is we're giving in what's called an objective function, and we have to figure out what values of x and y will maximize or minimize that equation given all these constraints or limitations that are put on it. So as I just mentioned, constraints are limits or boundaries. So there's what's containing or limiting our answer choices. It's not an infinite possible solution. It's going to be constrained or bounded in some way. And what we're going to be doing today, so sort of the overview of what our process will be, is we're going to create a feasible region which contains all the points to satisfy all the constraints. So if you remember when we solved systems of inequalities, we found the double shaded region. You can imagine our feasible region as the quadruple or triple constrained region or triple shaded area. So our feasible region will have more than just two linear equations that bind it. It'll have a bunch or make it bound. It'll have a bunch of different equations that make it a smaller or a more contained area, and that will be called our feasible region. So I drew a little visual here. These dashed lines you see faintly are that represent the constraints that are being put on our objective or to satisfy our objective function, and the shaded area is the feasible region. So we have the constraints are the lines, the shaded area is the feasible region. We'll create this today using our skills from graphing inequalities. So all this is just a more complicated set of our system of inequalities. Again, tying this back to what our goal is for this, we have to do or solve linear programming problems. We're going to graph our constraints, create our feasible region, and then figure out which values in this feasible region will maximize or minimize our objective function. So our objective function is the model or equation of the quantity we are trying to maximize or minimize, which in a lot of the problems we see today or in this lesson are going to include things like cost and profit. So you want to minimize cost or maximize profit. So our objective function will be not one of our constraints. We'll have a list of constraints, then we'll have a separate objective function. And that objective function is what we're trying to maximize or minimize. The way we're going to do this, so I'm giving you sort of the overview of how we're going to approach these problems and sort of front loading a lot of the vocab and information. But what we're going to do is graph our constraints, create our feasible region. Then one of the key things for today's lesson is that our maximum or minimum value for our objective function is going to occur at one of the vertices, or corners or intersections, however you want to think of that, of the feasible region. So we don't have to try every single point in the feasible region that we create into our objective function to figure out the maximum or minimum or how to maximize or minimize it. What we're going to do is graph this, find the 4 key intersection points or 4 or more or 3 or more intersection points, and figure out which one of those coordinates will maximize or minimize our separate objective function. So again, just one thing I noted on the paper but didn't say aloud, this works for linear functions. If we had a quadratic or an absolute value or something like that, it might work slightly differently. So just a reminder, this is for linear functions. This is linear programming, not for all functions. So let me flip the page and show you an example of what I've been describing thus far. So again, just if you can email me and let me know you're listening, kleary@k12.somerville.ma.us. I do want to make sure you guys are listening to these notes, so please send me an email really quick and let me know you are listening. So one example, or the example I'm going to start with, asks what point in the feasible region maximizes p for the objective function p equals 2x plus y given the constraints x plus 2y is less than or equal to 5, x minus y is less than or equal to 2, x is greater than or equal to 0, and y is greater than or equal to 0. So again, these are our constraints. These are the things that are going to bind or create our feasible region. They're the boundaries that will create our feasible region. We're going to find all the vertices or points of intersection of these 4 inequalities to see which one of those will maximize our objective function, which is right here. We're going to graph these and then plug in points to our objective function here. So our first step, I'm going to try to give myself plenty of room over here, so I might slide this over a little bit more. Our first step is going to be to graph the constraints. What you may want to do is put them into slope-intercept form if you find that helpful. So write in slope-intercept form. So I'm going to rearrange these two first ones real quick. X is greater than or equal to 0 and y is greater than or equal to 0. That's just a vertical line shaded to the right, horizontal line shaded up. So I'll deal with those after, but these I'm going to rearrange so I'd have y is less than or equal to negative 1 over 2x plus 5 over 2 or 2.5, however you want to think of that. This one will be y is greater than or equal to, because it flips when you divide by the negative, x minus 2. So again, if you want me to work through these, remind me in class. I can show you how I ended up with those, but I just rearranged them into slope-intercept form so that I can graph them. So now I'm going to go ahead and do that. So I'm going to make my feasible region x-axis, y-axis, and I'm going to graph 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. Oh, did I skip one? I did. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So first thing, I know x is greater than or equal to 0 is this vertical line along my y-axis. Y is greater than or equal to 0 would be this line along my x-axis. I'm not going to graph those because I just be going over my axes, but just know that those are two constraints that we will account for in just a second. So I'm going to graph these two problems. So I'm going to say these go by 1, 2, 3, 4, 5. So I'm going to use the half marks to graph 2.5 as my y-intercept. So I'm going to go up to 2.5 right here. And I'm going to graph down 1 over 2, down 1 over 2. So this is 1, not that, sorry, down 1 over 2, down 1 over 2, and that's my first line there. And then I'm going to graph my second, so sorry, I'm going to draw the line through there. It's solid because it has the equals to line, so I'm not worried about that. My next line starts at -2, so I'm going to extend this really quick. This will be -2 down here. And I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and then up 1 over 1 more. And again, this is also a solid line because it is also equal to. So I graphed my two lines. Now I'm going to shade. So I remember this one is less than, so I'm going to shade lightly, or I'm going to shade, mentally figure out where I'm shading. If it helps you, you can do the light shading. So you do the light shading this way, and then this one lightly shades above, then these two also shade to the right and above. What ends up being shaded is this bounded section here, because both x and y need to be greater than the other equation. This one needs to be less than, this one needs to be greater than, so you end up with that shaded area. So that ends up being our feasible region, and that's our second step. So we're going to shade our feasible region. Our next step, so if you remember from my key point, excuse me, on the last page, our maximum, or the point that will maximize our objective function here is going to be at one of the vertices or points of intersection. So what I'm going to do next is determine the coordinates of the vertices. So of the feasible region, sorry. So I can visually see these here, so I'm going to list them out. I have the point 0, 0 right here because that's where my x and y axis intersect. Then I have the point 0, 2.5 because that's where the x is greater than or equal to 0 intersects with y is less than or equal to -1/2 x. So on. So that's another one. I have this one here, which is going to be at 2, 0. And then I have this last point of intersection here, which is actually, I can see this here, and I know because I've solved this one out before. This is at the coordinate point 3, 1. So I know that last coordinate point is 3, 1. One thing I want to note is if you can't see this when you're graphing visually, you may need to solve algebraically. So I might have to solve this system algebraically to find that point or that vertex, sorry. So I'm going to note that you may need to solve for vertices algebraically. In this problem, we did not need to, but don't think that that will never happen. So now I've identified my maximum value for P is going to be at one of these 4 coordinate points. So I'm going to substitute these into the objective function. So I'm trying to see which one of these, when I plug it in, will give me the largest value for P. So I'm going to say P, in this first one, P equals 2 times 0 plus 0, which ends up with P equals 0. Sorry, P equals 0. The next one I plug in, I get P equals 2 times 0 plus 2.5, which ends up with P equals 2.5, because that becomes 0 plus 2.5 is 2.5. So again, I'm just plugging these values in for x and y here. So I have my x and my y values. The next one I get P equals 2 times 2 plus 0, which ends up with 2 times 2 is 4, so P equals 4. The last one, P equals 2 times 3 plus 1, and that's going to be 7. So now I have the 4 possible values. I'm just picking out which one maximizes P or profit. So I'm going to select P equals 7. So my last step is to identify and write solution. So my solution would be P is maximized at the point 3, 1. With a value of 7. So that is my answer. It depends on the context of the problem, but they could be asking about what x and y values. They could be asking what the actual maximized profit would be. But this encompasses both those possibilities, so it tells you the coordinate and what the maximum value of P would be. All right, make sure you write down any possible questions, comments, or concerns you have so we can go over them together in class.